All right, so guys, next thing we want to talk about here, we have a few terms that we're going to be utilizing for systems of inequalities. Again, at least a couple of these I know that we've seen and used before. A couple of them might be kind of new, but pretty obvious to also figure out, I suppose. First up, we're going to talk about the vertices. We define vertices as the points of intersection that refer to the solution of a region. So if we were to look down here at figure A, what we have on the left, please understand that kind of the common misconception here with vertices is that people say, oh, it's just wherever the inequalities cross, that's going to create a vertex. And that's partially true. But if we were to look at this dotted line and this dotted line, please note that that right there where they cross, that's not a vertex. Because that's not part of the shaded region. Does that make sense? When we talk about the vertices, they have to be bordering the shaded region. Are we clear on that? Because vertices are solutions, or at least they're what we call our extreme points. Again, a lot of this is based on where we're going tomorrow when we're trying to find the maximum, try to find the minimum of these values. So again, understanding where the vertices are located, we know what vertices are. We just have to be disciplined enough to realize that when we talk about vertices, we're talking about of the shaded region. Again, these would be the vertices in part B. Part C, there would be no vertices. All right. So next up, we have what we refer to as the bounded solution. So a solution set that is defined on all sides by an inequality from the system. We also have the unbounded solution, which is a solution set that is not defined on all sides by an inequality from the system. So to try to clear up what that means, I think that looking at a sketch is probably going to be the easiest option. A bounded solution, exactly as the word bounded would imply, is that it's completely contained, right? An unbounded solution, it's not completely contained, and the shaded region is going to infinity, either positive or negative. Does that make sense? So what we have here in figure A on the left, it's absolutely, it's defined on all sides is the way we say it. It's contained. It's kept within this quadrilateral. That within the interior of that quadrilateral, that's the shaded region. That's our solution. Whereas in part B, looks like this shaded is going to continue to go to positive infinity. It's just going to keep on going and going. It's never going to stop. Never, ever, ever going to stop. Okay? We see the difference between bound and unbound. Now we're going to use both. Definitely use both. I would say, honestly, I don't know. I mean, it's close, but I would say that the unbound is probably a little more common with what we do, but I don't know if that's even true or not. It's pretty close. And then finally, we have the no solution. So remember when we have when we had systems of equations, we said that the vast majority of the time we came up with one solution, but it was possible to have an infinite number of solutions or no solution. So we said that when no solution was present, that was because the lines literally were not crossing, which, as we're well aware, we call those types of lines parallel. So if that situation is presenting itself, how is that going to differ, I suppose, or change, or what's that going to look like if we had inequalities? So if we had a shaded region over here and a shaded region over there, we know that our solution is going to be where the shaded regions overlap. Do these overlap? They don't overlap. Therefore, there is no consistent solution. Does that make sense? All right. So, guys, what looks different about example number 3 that we're about to do? There are two inequalities, right? So we have two inequalities, which they are together as a system. But as far as how we're going to be successful here, we're going to graph one, we're going to graph the second, kind of as if they were separate from one another. But now when we're doing our shading at the end, we're only going to shade where it satisfies both of these inequalities. All right. The other thing that looks different about these, are these in graphable form right now? And we could make an argument that we could figure out how to graph them based on what you see, but I would say that we probably want to alter what these look like here just a little bit. So if we were to take a look at this top one, I'm going to try to color coordinate. I'm just going to recopy it down here. X squared minus y less than or equal to 1. I'm trying to get y all by itself, so I'm going to subtract the x squared over like this. Then we have to divide everything by negative 1. So we're going to get positive y here, positive x here, negative 1 there. What do I have to do? Remember to do with my sign though? We have to switch the sign. So one thing that I do want to be very clear on, again, this is now more of a graphical form. And I definitely dropped the fact that x was squared. Sorry about that. But do we understand now? Again, it kind of presented itself in a different fashion here during second period. A student was saying, yeah, couldn't I just add the y over to the right and then subtract over the 1 over to the left? Could we do it that way? And the answer is, of course, yes. And then the question, well, what about the whole sign switching? Remember, you only have to switch the sign if you're multiplying or dividing both sides by a negative. So actually what the whole switching the sign thing is doing is it's taking that into consideration. What we're really doing, yeah, we're moving the y over here, we're moving the 1 over there. So in order to just, I don't know, what we feel more comfortable kind of traditionally doing is that we have our isolated variables on the left, right? So, go ahead. By a negative, yeah, we have to switch the sign. Yep. So what we're saying is that, and again, I remember this in years past, that there were some students that were just brave enough to say, like, yeah, I know that when I'm supposed to switch the sign, I get it, but nobody's ever explained why that is. So again, please understand that that's exactly the reason why, is that we're trying to keep these, again, when the left side and the right side are equal to each other in an equation, it doesn't matter what's on which side. Now that we have greater than, less than, creeping in here, it is very dependent. So y has to be on the greater than side, whether our inequality is flipped or whether it's this way. So hopefully that didn't cause more confusion. But we're going to do the same thing here with the second. We have x minus y greater than negative 2. When I subtract the x over, negative y is greater than negative x minus 2. Once again, dividing everything by negative 1. Another situation where we are going to switch the sign, positive x plus 2. So we have the red inequality, which is quadratic. We have the blue inequality, which is linear. Do we feel like we know how to graph these things from here? I think so. All right, so the red one. This is the parent function for a parabola, but it's been shifted down 1 unit. So my vertex is here at 0, negative 1, which means if I go right 1, up 1, left 1, up 1, right 2, up 4, left 2, up 4, right 3, up 9. So let's count that out. 1, 2, 3, 4, 5, 6, 7, 8, 9. Left 3, up 9. Like that. Okay. I'm about to draw on this parabola. Is it going to be dotted or solid, please? Solid once again. Now we have two schools of thought, I suppose. We have two options. Could I do the testing and determine which way I'm going to shade right now, as I only have one graph up there? Sure. Some people like to do it that way. Personally, I am going to say that I generally like to figure out the shading at the end. Okay? If you're, I want to stop right here and figure out if I'm going to shade inside or outside, please do it that way. Like I said, I'm not teaching you this for the first time. Right now we're remembering how stuff works. So whatever worked well for you last year, keep doing it that way. I'm okay with it. Let's go ahead and look at the blue, the linear aspect. Our slope is 1, the y-intercept is 2. So we're crossing the y-axis at 2, up 1 over 1, down 1, back 1. So before I draw this in, what type of line am I about to sketch? This is going to be a dotted line, isn't it? Looking something like that. All right. How do we feel about this process so far? Okay. No answer means great, right? Okay. So we're going to test a point. You know where I'm going. With the origin 0, 0, we always have to question, though, is that actually an option? Were either of my functions going through the origin? The answer is no, so that means that we can use it. So if I were to test the origin 0, 0, I'm going to put a 0 in place for y, greater than or equal to, 0 in place for x, minus 1. Is that true? Is 0 greater than or equal to negative 1? It is. So I know that in relation to that red parabola, I'm going to shade toward the origin, which is in the interior. Okay? Now, I could go in here right now and shade that whole thing, but I feel like we'd be, having to erase stuff later on. So I'd rather just shade once. Again, my preference. Some people shade really lightly wherever, and then they shade really dark where the overlap happens. Again, I'm okay with that. That works. But on a smartboard, I have really hard time controlling if it's lightly shaded or darkly. Yeah, you get the idea, I think. So again, testing down here with my linear, put a 0 in place for the y, less than 0 in place for the x plus 2. Is this true? Is 0 less than 2? Also true. So that means that in both the red parabola, I'm shading toward the origin. The blue line, I'm shading toward the origin, which means that I'm shading this region here. So how would you describe that? Bounded, unbounded? That's bounded. Again, we're not going to infinity or anything like that, so this is the entirety. All right, so we have example number 4. What's different about this one, please? There are 2. Again, we're not, other than that, honestly, we're not really doing much different. Wait, did I say there are 2? I meant there are not 2. It's weird how it makes perfect sense up here and then the exact opposite comes out of my mouth. That's great. Yeah, so anyway, there are not 2. We have 3, but we're actually going to treat this the exact same way. Again, literally the exact same way. We're going to want to get these into graphable form. So let's see, if I were to subtract the x over, divide everything by the -1, do you agree that's going to give me y? Got to switch the sign, greater than or equal to x minus 4. I know that we're doing multiple steps mentally, but I think we can handle that. The second inequality, the 3x plus y less than or equal to 2, all we have to do is subtract the 3x over. So is this a situation, if I'm doing this, subtracting the 3x over, do I have to switch the sign here? Do not have to switch the sign here. So still y less than or equal to, now we have negative 3x plus 2. And then finally, the last one, x greater than -1. Nothing changes. We already have the variable isolated. So I should be a little bit more clear on this. What we just did, putting that into graphable form, did we have to do that? Was that mandatory? No. Again, could we have graphed, because these are all linear, could we have graphed these based on like, no, we could go x-intercept, y-intercept. I mean, you could easily draw in these graphs. I think most of us feel most confident, I suppose, with slope-intercept form. But here we are. Let's go ahead and give this a shot. The red one, the y-intercept is at -4, so down 1, 2, 3, 4. My slope is +1. What type of line am I about to draw, please? Solid line? All right, looks something like this. Once again, if you want to figure out the shading situation right now, please be my guest, but I'm going to wait till the end here. We also want to go ahead and draw in the blue line. So y-intercept is at 2, my slope is -3. So I'm going down 3 over 1, down 3 over 1, down 3 over 1. Do the opposite, up 3, back 1, up 3, back 1. Dotted solid line. What are you going to tell me, please? Solid line, looking something like that. Yeah. Crooked, better make that point bigger because I almost missed it. Okay. And then finally, x greater than -1. Horizontal line, vertical line. Vertical, we have to go through the x-axis at -1. So this is the x-axis at -1. So I'm going to draw a vertical line through. What type of vertical line am I about to draw, though? It's going to be dotted. Something like this. All right. So you may have gone about this problem a little bit differently and done the testing in the shading as you went. I'm choosing to do it at the end. Hopefully we're okay with that. Is the origin an option for us to test for all 3? Sure is. So if I were to do that here, I put a 0 in place for the y, greater than or equal to 0 in place for x, 0 minus 4, -4. What are you going to tell me? Is 0 greater than or equal to -4? Sure is. So that means that in relation to that red line, I'm going to shade toward the origin. All right, now for the blue line. Same story, put a 0 in for the y, less than or equal to 0 in for the x. 0 plus 2 is going to be 2. So again, is 0 less than or equal to 2? It sure is. So in relation to the blue line, I'm also going to shade toward the origin. And then finally, for the green line, if I put a 0 in place for the x, greater than -1, 0 is greater than -1. That's also true. Please don't get the wrong idea. I know that that's 2 problems in a row to where everything seems like it shades towards the origin. That's not always going to be the case. But here we again have another bounded solution with the shading looking something like that. Once again, the vertices, if we needed to identify them, would be in these locations. That's going to mean a lot more starting tomorrow.